Hello, and welcome back to the Aimless Electron. This episode is part 3 of the large format LED screen project. In the last episode, I went over the higher level details of the hardware that we used and how we put those things together. And I'll mention that one of the things I left out was how we powered those screens. I used two of these 350 watt, 120 volt AC to 5 volt DC converters. And they're pretty cheap off of eBay. And I probably could have gotten away with one of them. I used two so that we had a little bit of redundancy and we didn't overdrive these in case something happened. In this episode, I'm going to talk in more depth about the design of the FPGA, which I did in VHDL, the software that went onto the ESP8266, which was written in C, and the software that went onto the tablet to capture the screen and push it to the ESP8266, which was written in C#. Now, this isn't going to be a tutorial on how to program in any of those things. It's just going to show you what went into them. So stick around and let's go over to the whiteboard and I'll show you the parts that went into the FPGA. So this mess is the FPGA design. It's actually broken up into 7 chunks here and a couple registers. Let me identify those real quick and then we'll go into a little more detail about how it all tied together. First, we have our SPI device, which was just responsible for receiving the data first. It talked to the command decoder, and then it talked to the matrix driver, the V-line driver, up to 48 of the pixel drivers, and because we had 48 rows, and then the memory controller, which talked to the SRAM. There were also 2 integer registers for storing the number of rows and columns, and then a color lookup table, which was 96 8-bit registers. 8 bits because we had an 8-bit color, but we were translating it from a 5-bit color. So we could address up to 32 per red, green, or blue. Now let's go how the data flowed through here. First, it came in from the ESP8266 over SPI. From there, it went over a 32-bit bus to the command decoder, and the command decoder would look at that 32-bit bus based on the ready signal. The command decoder looked at the 32 bits for most significant bit and decided if it was set that it was a command, or if it wasn't, it was color data. Now, the color data, like I said, came in 15-bit chunks. So we actually had 2 pixels per 32-bit register. But we only ever looked at the most significant bit for the command. If it was color data, it just got stored in the SRAM. If it was a command, you would either write to the columns, the rows, or something in the color lookup table, or tell the matrix driver to draw the screen. There's also a memory bank command because we took this SRAM and split it in half. We had a low side and a high side. That way we could be writing to one area and reading from another, so we could double buffer. The matrix driver just took whatever this memory bank was as a starting address, fed that starting address out to the V-line driver, and then it counted, based on the number of rows, how many more addresses it had to skip before the next one. Once the V-line driver was able to draw its vertical line, it would signal the matrix driver that it was ready, and the matrix driver would feed the V-line driver the next address. The V-line driver, once it had what address, it would pull in the color memory, or the color data from the color lookup table, hit the memory, and translate those values from 5 bits in here to the 8 bits that we actually wanted to use. Those 8 bits would be fed out to the pixel drivers. The pixel driver's job was only to take the bit and turn it into a signal that the ws2812 understood. From there, the data would go out to the 74HC245 line drivers and then off to the screen. The only other external component we really had here was a global reset, and when you push this, it caused everything to go back to its initial state, or its very starting state, so that in case some weird data went through it, which happened a bit, you could start over without having to power it down. Now I'm going to take a look at some of these devices in a little more detail. So this is the SPI block. It's pretty simple. It just has the 2 inputs, the master out slave in for the data, and the S clock, and these are both coming from the ESP8266. It attached to a 32-bit register, which it just started counting at 0 and went all the way up to 31 every time it got a clock pulse. It finally had a ready signal when it reached the end and had stored the last bit for whatever stage went next, and it would read that. The system clock up here was used to actually make sure that if there wasn't a clock pulse every at least 1 millisecond, it would reset the count so it could start over, and it was kind of like a watchdog time for the SPI. Here we have the command decoder. It's a little more complex, but I'll try to go through it quickly. It gets its data from the SPI device, which starts everything off by pulsing the ready signal. If it receives that ready signal, it stores this 32-bit bus in its own 32-bit register and checks the most significant bit. If that bit's a 1, it's considered a command where it'll either write to the rows, columns, color lookup table, or cause a draw. If it's just color data, meaning that most significant bit is 0, it'll take the rest of the data and split it up into 2 pixels because it's only 15 bits per pixel. So it'll take the 30 through the 16th and the 14th through the 0th and store those as 2 pixels. And it'll just write that out to SRAM. And then it'll keep track and update its own internal address counter. If it receives a draw command, or if the number of pixels it stored equals rows times columns, in which case it'll send this draw command out automatically, it'll flip this memory block indicator, which tells the next stage either to look at the high memory addresses or low memory addresses, and it will also reset its address counter for what memory area it's writing to. Next, let's talk about the memory controller. It does have a lot of inputs and outputs, and I'll try to go through them and make it make sense. But its main job is just to take the data that should be written or read and correct the timings for it to go out to or come in from the SRAM. First, we have the read signal in and the write signal in, and depending on what you want to do, you set either of those high. And then it also has signals out to indicate that the read has been done and is ready to be read, or that it's ready to be written with the wready command or signal. We have also a write address and a write data bus, and then a read address and a read data bus. The read data bus is actually an output where the rest are all inputs. On the SRAM side, it just has the write enable, the read enable, and the address signals, and then the two-way data bus. How this works is if you set read ready, it'll take whatever data is on the read address and store it until it is actually able to read, and then send that data back and set the read ready signal high. On the write ready, that's going to stay high until you're actually trying to write, and when the write is finished, then it'll set that write high again. And you again just signal it by saying the write high when you have the write data and the write address present on those buses. The next piece we have is the matrix driver. Its job is kind of to coordinate the drawing of the entire screen, column by column. When it receives the draw signal, it takes a look at the memory block signal, and if it's a 0, it starts at address 0. If it's a 1, it starts halfway up, in other words, like 32K addresses up. It takes a look at the number of rows, and that's how it knows how far to jump for each address. Starting at 0, it'll set the start address and signal a draw to the next stage, which should be the VLine driver. And once the VLine driver has drawn its column, it'll send a ready signal back. When this gets that ready signal back, it'll increment its columns count and based on the number of rows, increment the starting address. In other words, if it's got 48 rows and it started at 0, the next address will be 48. It'll go through, and when it reaches the number of columns that it's supposed to draw, let's say there were 10 columns and it's reached number 10 and got that ready signal back here, it will then signal ready again and the process will start over. The VLine driver starts when it gets a signal on its draw line. It looks at the start address and gets the data at that start address by talking to the memory controller. It then takes that data that it gets and looks at the first 15 bits instead of all 16. And then for each 5-bit chunk, it references the color lookup table to get the 8-bit green, red, and blue values, stores that in a 24-bit register, and does that for however many rows there are. If there's 48 rows, it does it 48 times. And in other words, if the starting address is 0, then the next address is for row 1, and it goes all the way till it reaches the end of rows. When it's finally done with getting the data for each row for one column, in other words, 1 pixel, it clocks that data out to the pixel drivers, up to 48 of them. Once that data has been clocked out, it sends the ready signal back. Now the reason that we clock it out is because we rely on 3 clock pulses going through before we are done instead of waiting for a ready signal back from each pixel driver. The final link in the chain here is the pixel driver. It's really simplistic, and you can have up to 48 of these, so they run in parallel. It's got a data in, a clock in, and a data out, and its job is to convert a bit into a signal that the ws2812s can understand. This is all clocked by the previous stage and doesn't have any kind of feedback. The way it works is if the data in is 1 and continuously 1, on the first clock pulse the data out goes high. And if it's still 1, remains high for the second clock pulse, and on the third clock pulse it drops low. And that's, again, for about 800K to 1 megahertz. If the data in is low, on the first clock pulse, the data out goes high for 1 clock pulse, then returns to low for the last 2 clock pulses. And that's about all it does. Finally, we have the display driver. It just takes all the constituent parts and hooks their signals together, and then exposes the appropriate signals to the outside world so that you can hook those signals up to the appropriate pins on your FPGA. It has inside of it the SPI, the command decoder, the matrix driver, V-line driver, memory controller, the 48 pixel drivers, and then the rows, columns, registers, and the color lookup table. Now on the outside, it has the 48 lines out to the screen, the address and data and control lines for the SRAM, and then the SPI in, a reset in, and a ready out. By the way, the ready out is what's connected directly to the command decoder, which when it is ready for more data, it'll signal that to the ESP8266. I'd like to make a point that most of the buses that you've seen in here have been 16-bit, except for the SPI bus, which was 32-bit, the color lookup tables, which had an 8-bit data bus and a 5-bit address bus. And then finally, of course, the 48 lines on the bus for the data out. Next, I'm going to talk about how I programmed the ESP8266. So this is a diagram of the code that went into the ESP8266. I'm not going to look at the code itself because that would be out of scope of this video, but I will post a link to it at the bottom. Inside the ESP8266's API, there's a start method defined that gets called when it starts up. That's where we put this code. This set the system clock to 160 megahertz instead of 80. It called init on the UART, which set the baud rate, which we used for some debug information. Called init.io, and in our init.io we set up GPIO pin 5 to be an input with an interrupt handler on it. That interrupt handler, in its callback, checked to see if GPIO 5 was high, and if it was, it sent a ready signal back over TCP and then cleared the interrupts. The point of that was we hooked up the FPGA's ready signal to that so we could signal the tablet when more data was ready to be sent, or when it was ready to receive more data. Next, we set up the SPI. The SPI just is set up by setting it to HSPI and pretty much just setting its clock dividers to set the speed of it. We had 2 modes that we could set up the Wi-Fi in, and we used soft AP mode as our in-field, our actual usage, and station mode as a way to debug it, so I could hook it up to the local network that my computer's on and push data to it and debug things that way. If it was in station mode, we also set up an event callback. That event callback just pushed out data through UART saying that it was connected to some access point and what its IP address was, and then called this init TCP server. I'll get to that in a second. To set up the init station, or to set up the station mode, you just set it to station mode and set the SSID and the password for the SSID that you want it to connect to. In soft AP mode, you just set it to soft AP mode, you set its IP config, like what its IP address should be, what its net mask should be, what its gateway should be. You set what SSID you want to use and a password if you want to use one, and then some other configurations like what authentication mode you want to use, how many devices can connect, if you can see it, if it's hidden or not. And then in that mode, I called init TCP server explicitly. Oh, to set up TCP, we set the server type to TCP, we set what port we want it to be on, and then we set that callback. It waits then until it receives data. Now this is where it becomes a little trickier because there were maximum receive sizes and maximum send sizes, and I wanted to get this thing to go as fast as possible. So what I did in the TCP receiver, which could receive up to 1400 bytes at once, is I split it up into 16 32-bit chunks. The reason I did that is because that equals 512 bits, which is how much the SPI can handle in its register at one time. So I break that up, and once I have 512, I send that out over SPI, and if there's anything left after that that didn't fit in that 512 range perfectly, then I send the rest of that chunk. And finally, in the SPI mode, I wait for it to be ready. I send the bytes out that it received, starting at address 0, actually this is 040, and then I skip it skip 4 bytes because I'm doing this in 32-bit chunks. And finally, I transmit the SPI data, and I do that until no more data is left to receive in the callback. And that's how the code works in the ESP8266. Now I'll take a look at the code that's in the tablet. So this is the main screen that we use to capture things. Obviously you have your address and your port that you can connect to, and the size of the screen, in other words the pixels, as well. But once those are set and you're connected, you can't change those until you disconnect and reconnect. The gamma, however, is live, and you can change that while you're displaying and capturing. Right now I'll just demo what the screen looks like that you use to capture. It's this little green framed window which you can resize. And of course, because we've got kind of an elongated screen, the more rectangular, the more even things look. This is just a little demo window. The gamma doesn't actually affect it, and the update rate is kind of slow just to keep things moving quickly. I'm not going to actually show any more of this, but I would like to explain how I put this together. This is done in WPF, and that means that this is all written in something called XAML. How I made the screen was removing all the Windows controls, the Chrome basically, creating a border, and then setting the background of the screen to transparent. What that usually does, however, means if you click inside of it, you're not actually grabbing the screen. So there's actually an overlay here that's got a very, very light transparency over it. You can't really tell, but it is slightly darker in the center of this. It just makes it a lot easier to grab than trying to grab the borders and drag those around. Next, I'll go over the flow of the code. I'm not going to go into the code itself, just the diagram. So this is the code diagram for the main view model class, and I'll explain what that view model thing is at the end. For now, it has a constructor that sets a default IP address and port, sets up the default gamma lookup table to adjust the color brightness, creates a timer to show the frames per second and sets its event handler, then creates an event handler for the connect and run events, which are bound to the connect and run buttons that you saw on the main screen. For the elapsed event handler, all it does is display the FPS and then reset the frame counter. For connect, if it's already connected, it disconnects. Otherwise, it connects to the TCP server, or at least tries, and then creates a thread to receive that ready signal from the ESP8266. When that's received, all it does is set a flag that says received is true, or ready is true. When you click run, if you're connected and you're already running, it stops the current capture, closes the capture window, which is that little green, and stops the frame per second timer. Otherwise, it starts the timer, starts that window up, and sends the rows and column size, creates a color lookup table that gets stored in the FPGA and sends that, and then starts capturing in a new thread. That capture is started by calling the send capture. Inside send capture, there's a while loop that calls all this code. It gets an image from the capture window, and that's done by calling a screen cap just in the area of that capture window, and that's automatically scaled to our rows by columns size. Then it calls this get bitmap bytes function, which creates a byte array from that image, pixel by pixel. It also converts the 24-bit color in each pixel to a 15-bit color based on the gamma lookup table. Finally, when that ready flag is set, it sends the bitmaps out, or the byte array out to the TCP connection, and increments the frame count and resets that ready signal, or that ready flag. Real quick, the gamma lookup table is based on a for loop that counts from 0 to 255. We're not setting different gammas for red, green, and blue. We're using the same one for all three because we kind of ran out of time. For the calculation on that, we create an entry for the table based on I divided by 255 to the power of gamma, then times the maximum gamma, and then we basically offset it by 0.5. To generate the color lookup table that's stored in the FPGA, we're actually creating a 4-byte chunk that contains the command for which color we're sending and the 5-bit lookup plus the 8-bit color itself. And that 8-bit color or 5-bit lookup is just generated by taking the 8-bit color and right shifting it by 3. So real quick, the view model thing that I'm talking about is part of a design pattern called model view model used in WPF programming quite a bit. And it just means that your code for your UI or your window or whatever is completely separate from the code that does your business logic, and that's inside of the view model, your view being the UI. You just use bindings to handle the events and connect, like, say, a text box to a text property or a string property. So if you see that in the code, that's what you're looking at. There's a lot of documents out there, but it's way out of scope for this video for me to go into that. That's pretty much it on how the code on the tablet works and what it looks like. Next, I'll go over real quick how to set up the Eclipse environment to program the ESP8266. So this is how to set up the Eclipse environment for Windows, at least, to push software to your ESP8266. Obviously, you'll need to download and install Eclipse if you don't already have it. Next, you'll want to grab the min.gw compiler. Once you've got that, start the setup. It's a pretty straightforward setup. I already have it installed, so I'm not going to go through this again, but I will say it's best to leave it at the default directory, and you also don't need to install support for the graphical user interface. Next, you'll want to grab this unofficial development kit and just click download. It'll probably pop this up and show you it'll look something like this, because I think it detects what you're running. So you click that. That's a little bit bigger. It's something like 150 megs. Once you get going in that, run the install, accept it. You can accept all these tools and let it install to the CExpressif. That one's actually really important because there's other things that look to that directory that you don't set up. So I'll let this install real quick and I'll be right back. And that's it. The next thing you'll want to install is, or at least download, is this Expressif DevKit install pack. Now, even though you're supposed to run that Windows batch file as an administrator, sometimes that doesn't work, so you have to open it up and actually, well, comment this stuff out. And once that's done, you don't have to worry about it anymore. It should run just fine. It makes a couple other things inside the setup for your environment a little bit easier. Finally, start up Eclipse, and this is pretty much the last step. Once you have Eclipse started, and I already have this, so I'm just going to go through it again. You can go to Import from the File menu, select General, select Existing Projects into Workspace, click Next, then browse to your C drive, and you should see this Expressif folder. Expand that, select Examples, click on OK. All these things should be checked here. Mine are already installed, so that's why you don't see a bunch of them checked. Hit Finish, and it will install all these packages, which may seem like overkill, but to be honest, they're great when you're trying to figure out certain things, like how to do interrupts or how to talk to different things over TCP or UDP or UART, because you can just copy them in, and it has all the header files you'll need. When you create a new project, I will say that you'll want to come over here to the make targets and add make targets. You can copy the text again, but these will be used to do things like flash it and build it. These depend on what's in your make file as well, which is going to be important for setting certain things up, like the baud rate that you want to upload to your ESP with, and what COM it's attached to. If when you've connected, like, the USB to serial adapter from FTDI or something like that. There may also be some other settings that you need to mess with for well, depending on what ESP8266 you have, the size of your SRAM, and if it's DIO or dual IO or quad IO, that'll be stuff that you'll have to look up on your own because I can't tell you what it's going to be here. But you change most of those settings inside the make file. You can pretty much copy the make file from any of these other projects and just, change what names that you need to change inside here. That's pretty much it. And once it's done, all you should be able to do is click Flash, and as long as you're in program mode on your ESP8266, you're good to go. Well, that was a pretty long video, I know, so if you're still watching, thank you very much. That was what it looked like internally to build up the code. There was a lot to it. If you have any questions about it, please let me know. I know the code that I'm posting isn't going to be that pretty. We did run out of time. I've never programmed the ESP8266 before, and I've actually never touched an FPGA before. This is my very first time, so please bear with me when you see that. But if you do have any questions, feel free to ask them. If you have any comments or suggestions about how to make the videos better, send those along too. And if you liked it, give it a thumbs up, subscribe, tell your friends, and I'll see you in the next video.